Okay, so let's continue the artificial potential field. This is number 2, yeah. Okay, you guys can see my screen
Yeah.
and hear my voice and everything is fine. Okay, let's do that. So last time we explored the 2D algorithm of, we started it, of artificial potential field. Okay, so we reached the part for which we were building the repulsive force. Okay, so if we show this repulsive force very quick, yeah, so this is what we actually the point at which we reach or we finished last time. So basically this is a 2D map. If we look at it from a 2D perspective from above, okay, so this yellow stuff is the yellow portions are actually the actual places or locations of the obstacles. So as we said, we have two rectangular obstacles, this guy in here and this guy, okay, and we have two circular obstacles, and we learned how to build such a circular obstacle in MATLAB. And this is something that you should know. I may ask you about that, okay, how to build, an obstacle and stuff. Although in real life it's really given, but if you are in a company and you want to simulate what's in real world, then you should be able to generate a map with obstacles to build your algorithm and test your algorithm with. This orange and the green and semi yellow and stuff, sky blue, I'm sorry. So these the portions that are not yellow is actually the gradient, okay, or not the gradient, I'm sorry, is actually the values of the repulsive force. So if we go back to the 3D view, okay, so this point in here, for example, has 3 coordinates like what you see. So x and y are actually the coordinates of the 2D map. So this is a point in the 2D map, which is, for example, here 96 in x and 30.8 in 308 in y. And the value of the repulsive force at this location is 255.6. Okay, and we said that if you have a map like this, okay, half of the problem is to build the repulsive force in such a way so that if the robot started some way close to the map, it will be along this, slope, we can say. So if we imagine the robot is just a ball, the ball will slide down, but then it find a flat field on the map. This portion in here, this for example, this area here is just flat. Also, this area here is flat. Okay, so yeah, so the repulsive force, it pushes away the robot, but it doesn't lead it or leads the robot to the map. I'm sorry, to the goal. I'm sorry. Okay, so it just pushes it away. So what is the function or the force that will attract the robot toward the goal is actually the attraction force. So let's go and see what this attraction force will look like. Okay, so basically to draw such mesh, or map with 3D stuff, we use this function called mesh in MATLAB. Okay, so mesh of any array will draw this array in the way that you saw. This stuff here, it just keep it like this. Okay, it's face lighting, in figures, They assume there is a kind of light in front of the map, so you can see better. So it's something like this. So just ignore that. This will be given for you. Okay, but how to draw? Yeah, you should know that. This mesh stuff. And here is we can add a title to the plot. This is something in MATLAB. So here you see this title here. So we generate this using this command here, title of whatever. Okay, now we're gonna generate the attractive force. Okay, to generate the attractive force, the attraction force will attract the robot towards the goal. So the goal location must be known. Just like the repulsive force. In the repulsive force, the obstacle must be known. So we will build these hills around the obstacle so that the robot can slide down away from the obstacle. Now we need in the attraction force we need the goal location coordinates, so that we will build again this force around this point, the goal point, such that this goal point will be minimum. So if there is a robot around, it will slide down until it goes to this point. Okay. Okay, you remember, guys, there was, let me change this. So if we go back to the slides, yeah, the attraction force has some, where it is? Yeah, this zeta stuff here, okay? So let's call this zeta, not xi, that's fine. So this is zeta. So I think I forgot to change it. Again, this is not my code, as I said. Okay, I got it from GitHub. So the guy, instead of using zeta, this constant here, this parameter, not constant here, he uses xi. That's fine. So we're gonna change it to zeta, as to be consistent with the slides. Okay, so let's just change also it in the comments, and that's it. Yeah. And just very similar to the 1D example, okay? We said that in the 1D example, the F attraction force was equal to constant, which is zeta, multiplied by x minus g, the goal location in x. Okay, now it is very similar. We still have a quadratic equation, but this quadratic equation is actually a function in 2D. So let's do that in a separate file. Okay, so where is it? Quadratic function. So let's open up this file called the quadratic function. So for each section in that code, that very big code, I'm making some helper, some helper programs aside, so to understand this piece of code in specific. So here I will show you how to generate a function, a function that is function of two variables, x and y, and how it will look like if we plot it. Okay, where will be the minimum? It will be exactly similar to the one we did in 2D, which is just a parabola like this. So let's see. And why we should have a quadratic equation. Okay, we actually answered this question previously, that the quadratic equation has a minimum, and we saw that in 1D, but we will see it again in 2D. Okay. So let's assume we have a variable called x, it's changing from minus 100 to 100, and there is a step point 1. So this line here will generate a kind of array, 1D array. The first element will be minus 100. The second element will be minus 100 plus 0.1, then minus 100 plus 0.2, and so on, until we reach 100. So it has a lot of numbers, I would say. The goal is at 0. Okay. And here is I am building an attractive force, but this is just 1D now. It's just this is 1D, not 2D. I'm sorry. Okay, 1D, 1D convex quadratic function. So let's, you know, in MATLAB, guys, if you make a section, if you start a section or a part with this two comment sign, you can actually evaluate this part alone, separate from the whole file. So you just, you know, you just highlight all the content in that part, and you can just evaluate selection. Okay, so this will evaluate. So you see, guys, this is what we get, and we see. So this is a quadratic function in 1D. It's a function of one variable only, and as we see at the goal, we have minimum. We're gonna see the same but for 2D now. So this is 1D quadratic function. So let's put it aside. Let's get this guy in here. Oops. What? There is a trick to make the side by side, but it doesn't work for some. That's fine. We can do it manually. So Windows 10 has some trick to arrange, you know, Windows side by side, but that's fine. Okay, this is the 1D. Now let's go to the 2D now. I understand now. It's 1D, 2D now. Okay, this is 2D, and I'm gonna change it everywhere. Okay, so this is the 1D. Now let's explore how to create a function in 2D, in two variables, a function of two variables, 2D. Okay. So assume, you know, you have 600 rows. So let's say y is changing from 1 to 600, and 600 columns. So x is changing from 1 to 600. Then using this you know, nice formula, mesh grid, we generate two arrays. One is called x and one called y. And we said last time that using this function here, and of course we should know this as well, that x and y will be two arrays, okay, that contains the coordinates of the map. The y coordinate of any cell in the map and the x coordinate in any cell of the map. So please review, as I said, of course, I asked you to do that, to follow me fluently in that lecture. But anyways, so okay, now I will define the goal. The goal now has two dimensions. Here the goal only x, so just one number. Here we have x and y, so I must define two coordinates, x and y. So it's at x equal to 1 and y equal to 300. I'm sorry, y equal to 1 and x equal to 300, because we said that x is actually the columns and y is actually the rows, also in the previous lecture. I hope you studied this lecture very well. So this is actually y and this is actually x. Okay, now let's define another function that I called attractive 2D, because it's a function of two variables. X minus goal of 2 square plus y minus goal of 1 square. So just compare this one to this one. Here you have only one variable, so we have only one of those. But here you have x and y, so you just define it 2 times. Subtract the x coordinate from variable x, and subtract the y coordinate, which is goal of 1, from 1. Okay. Okay, let's draw it. So let's draw that guy here, that selection here, and see. Let's see what's the difference between that guy and that guy, the 1D. Oh, okay. Okay, that's fine. So basically, guys, I told you that the goal is at x equal to 1 near 0 here, and y equal to 100. So I'm sorry, 300. So if we see here, this should be the minimum value. So this should be the minimum here. You can imagine or not? Is it clear? Let's
Yeah.
do. Okay. It will be. I will make it more clear for you now. So I will change this to 300 and 300. So it's in the middle. Remember, x is changing from y is changing from 1 to 600. X is changing from 1 to 600. So the middle point should be 300 and 300. So let's do that again with 300 and 300. Yeah, that's what I was expecting, but I forgot that I changed the goal. So I said that the goal is in the middle of the map. So the middle of the map is actually the point of the minimum here. So if you imagine there is a ball somewhere around the goal, it will slide down until it reaches the goal, the minimum of this function. I hope you guys can imagine that, okay? It's just 2D. So here we have 1D. So you have just one point on one line, one axis, which is x. Here, no. Here you have the goal here has two coordinates, x and y. That's why it looks 3D, okay? And that's why actually why I name it in the beginning 3D and 2D, okay? But anyways, so here you have x, you have y, and you plot the magnitude or the values of the function in the z-axis. So that's why it looks 3D, okay? So this is how to draw a function in two variables, and this is how to create a quadratic function out of two variables. And based on that technique here, that very simple technique, you can get the minimum of that function at the goal, which is the required property for the attractive force. Okay. If we change that, let's bring it back to 1 and 300. This should change the minimum. Yeah. So the minimum would change it. Let's make it, for example, 1 and 1. So the minimum should be in that corner here. So let's make it 1 and 1. Look. And you can do whatever. All the time, you will have one minimum at the goal location. Okay. Good. So let's go back to our original example here. This guy. Yeah. Good. So let's see why I choose zeta equal to 1 over 700. Okay. Oh, actually, this was, I think, is the original value that I found in the code that I found on GitHub. But let's play with it. I said that this is an engineering choice. You can choose this value as whatever you want. So let's see why 1 over 700 may be a good value. Okay. So let's see, for example, yeah. So as I mentioned here, it's used to control the strength of the attractive force. Okay. Yeah. Okay, we'll try it when we add the attraction and the repulsive together, because we cannot check its value or why we choose one of the supernovae without comparing it to the repulsive force. So let's delay this for a minute. Okay, and let's go back to it after a while. Okay, so let's draw the attractive force for that particular map. This is a repulsive. Okay, we stop that here. So let's continue. Now we're gonna draw, yeah. So again, the attractive force doesn't look at the obstacles at all. It is something separate. Okay. Just look at the goal location and the size of the map. Okay, so here the goal location is at 450. So this is 400 basically, and this is 50 somewhere between this point and this point. So let's enlarge it, and you know, yeah. Maybe it's clear that it's in that point. I'm sorry, in that region, the minimum. We can change it a little bit. Let's increase it a little bit to see, you know, the curvature very well. So let's make this 150, for example. We're gonna make it back 50, and we're gonna see, okay, and we reached that point. So let's good. Yeah. Look, guys, it's going into. So maybe this is more clear, or clear that, you know, every point around the goal, which is here, has a value larger than the goal, and the goal is at the minimum location. I hope it's clear. Okay, I will, you know, just rotate it so you can visualize it better and better. Okay, any questions? So so this was the attraction force. 1 over 700 is a good value for zeta. We will do this study just after 2 minutes maybe. Okay, here I am just, you know, showing, I will show now the goal. So let's show the goal somewhere. So this is the goal. Yeah, let's bring it back, because this location is actually on some obstacle, so it's not valid. Okay, and so here is, I'm showing the goal over, you know, the map. Okay, and here is the goal. Nothing new. Now this is, you know, a very important step, which you add the attraction force and the repulsive force. And remember again, we need both. The attractive force is aware of the goal, but it's not aware of the obstacles. Okay. The repulsive force is aware of the obstacles, but it's not aware of the goal. So if it pushes away the robot can go anywhere. Okay, so we need to add them together. So we're gonna combine both characteristics together in one function, which is f. And this is what we're gonna see now. So let's draw that. Yes. So this is basically, you know, the addition of two functions. This plot here is actually a plot of an addition of two plots. We can say so. I hope I can have, yes. So just imagine these two plots is added together. I hope it's clear that this guy in here is just the addition of the repulsive force and the attraction force. So at any x and y here, we take the value of the repulsive force, the attraction force, then add it to at the same x and y, add it to the value of the repulsive force. This will give us, you know, a new amplitude for the f, total f. Okay. So for example, this you see, guys, this corner here, it was at 0, right? And this point is the same corner at 401. It has 400. When we add 400 to 0, it gives us 400. This point at the corner. I hope it's clear. Okay. This is, again, this corner is 0, but this corner has a value, I think maybe 100 or something. Yeah, 56. So here we have, I hope it draws something. Yeah, 50. Yeah, It's like it's not the exact point, but it's close to it, so that's a close value. So I think the idea is clear. In MATLAB, this is just the numbers. An array, this is an array. I'm gonna add it to another array. So what you're gonna do, if you add two matrices together, what you're gonna do? You add the corresponding element together. At the same row and column, the element one at some row and column plus the same element at the same row and column. Okay, you add them together, you get a new function or a new value. Okay, so this is clear. Any difficulty in this?
No.
Okay, Mr. Saul. Okay, so let's continue now. So this is just an arbitrary starting location. Just choose any starting location that's away from some obstacle. Okay, and now the most important part, which is the gradient, or the potential, the artificial potential field planner. We call it planner because you plan a path between a start and a goal. That's it. Sometimes they call it gradient based. That's fine. Artificial potential field is just a gradient. All are the same. Synonyms. Many names for the same stuff. And why they call it gradient? Again, in the lecture just before and also last lecture. In the last two lectures, we see that the goal is using the gradient, okay, and try to descend toward the goal. And we see that always the goal, the direction to the goal is in the opposite direction of increasing the gradient, or in the direction of decreasing the gradient, okay? We saw that, and we did it with using 1D, and I hope it's clear. So let's now go to the function itself. So let's go inside the function, step in. Yeah, this is a function. This is where the gradient descent will, actually happen. Okay, so just to create an array called route, okay, in which we will put any all the point by which the robot will pass through from its start to its goal location. Okay. Okay, the first point, of course, in the route, or the from start to goal, is actually the start point. This is our first point. And remember, guys, the speed stuff. So here I'm choosing the speed equal to 3. I think this is the best value. Okay, so let's go into, so we have some iterations. This is defined outside this function. For example, 100, 1000. This is, again, a user choice. And here, this is exactly similar to for 1D example. If we go to the 1D example, where is this one dimension example here? So let's go to examples side by side. So this is step here. It's similar to this, where it is. Yeah, this one. But you can just put it inside the loop, or in the conditions, that's fine. Okay. There's all the same. Here you have only one point. Okay, the current position and the goal. But here you have 2 points. Okay. So you have the goal location has 2 coordinates, X and Y, and you have the current, so this is the goal location, or the end coordinates, and you have the current position of the robot. Okay. So here you are measuring the distance between, or calculate the distance between those two. So let's go to the tablet to show you very quick what is this norm is doing exactly. So if we share the tablet screen, It will be very quick demonstration. You guys can see the tablet, right?
Yeah.
Okay. I have a problem with the tablet itself right now. For some reason, the OneNote cannot open. I don't know why. I think, what is that? Okay, okay. Yeah, here it is. So file. Okay, so if you have a map like this, you know, X and Y, and you have 2 points, okay? This has, let's call this X goal, Y goal, and this is X current, Y current. So this represents the goal location, and this is represents the current robot location on the map, okay? So this distance here, this distance, any idea how to calculate it? Any idea? It's very easy.
Subtract that.
No.
Just subtract the points.
Yeah, that's right. That's a possibility. That's a possibility. It's E. So one possibility, you know, let's call it I. X absolute X G minus XC plus absolute YG minus YC. This is what you meant, right? Or something different?
Yeah.
Okay. There is another. Yeah, there is another solution for it. Okay. Although they are not equal, they are different because this guy is actually calculating the distance like this. If we move in X first, they move in Y. So this is actually X absolute of XC minus XG. Of course, it doesn't matter because there is absolute. And this is absolute YC minus YG. So you move like this, then you move like this. But it's not this distance. This doesn't equal to this hypotenuse here doesn't equal to this guy plus this guy. Okay. So some people use, you know, the actual distance between the 2 points, which is a square root of X goal minus X current square plus Y goal minus Y current square. So if you have 2 vectors, let's talk MATLAB now. If you have 2 vectors, the first vector is X called 2 arrays, XG, YG. The second vector, second array, is called XC, has 2 elements, XC and YC. So the norm, this is a function in MATLAB called the norm, of both these 2 vectors, XC, YC, and XG, YG. The norm of these 2 vectors is actually equal to that thing in here. Okay? So that's why. And people usually prefer this kind of function. As I say, if you remember, guys, in the A star, yeah, in the A star algorithm, I said that we're gonna use in the A star, we're gonna use this guy, but for future lessons, we're gonna use this guy. But you can use both, by the way. I tried both, and both are okay. Okay. But people usually prefer the second one, the norm distance, not the hope distance. The first one is called the hope distance, or we can call it in that way. So let's now go to the MATLAB. This is clear, guys? This is clear?
Yeah, so norm just calculates the magnitude, right?
The norm is calculating this actual distance.
Yeah, I get it, yeah.
Okay, but this one here is actually calculate the distance in another way, but they are not the same mathematically. So it determines this length plus this length. It assumes that the robot will move in that way first, then this way. Here we assume that the robot will move directly in that way. And I know that at the end, the robot will move in such way, okay? But mathematically speaking, when you calculate something, it's better to calculate it that way rather than this way. Just from a math point of view. But the actual stuff that will happen in nature, the robot will move in that way. X then Y, or Y then X, doesn't matter. Okay. So let's go to, and you can do both. Just to make it, feel comfortable, you can do both. So let's go to the MATLAB now, again. Okay, so here you calculate the distance, the actual distance between the current location and the goal location. And if it's less than some tolerance, then okay, we reached the location. So just escape or break the while loop, and that's it. Okay. Otherwise, what you should do, something similar to the one dimension. You calculate, the difference between the current location in X and the goal location in X. Here only X is matter because this is 1D, but here in 2D, you do both, delta X, delta Y. Okay? So, delta X is equal to the gradient of the current position. How much this current position is far from the goal location. Here you are doing exactly the same, but now you have each point has X and Y. So you should do that X and Y. There is something that okay, there is that I forgot to mention. So again, here before the loop here, we calculate the gradient. Gradient equal to this stuff. Here you have a function that is function of only X. But if you have a function that is function in X and Y, then the gradient of this function will be also function of X and Y. Okay? So the output will not be one dimension anymore. The output is two dimension, just like this. Here, the output is an array, one dimensional array. But here, no, the output is actually two dimension. X, you have a gradient in the direction of X, and you have another gradient, another component in the direction of Y. Okay. Okay, so yes, so here is we calculate delta X, delta Y. Okay, this is equivalent to these two steps, is equivalent to that step here. Then we calculate, as we said before, this guy here. We calculate the direction. We are not concerned with the value or the absolute value of the gradient. We are more concerned about the direction, the negative or minus, whether to go in the direction of X or minus X, whether to go in the direction of Y or minus Y. So this step here is equivalent to this step here. In that step though, this delta direction X was either positive 1 or negative 1. We did this together many times. Okay. Here, delta direction X and delta direction Y, they will not be positive X and positive 1 and negative 1. No. They will be something less than 1 positive or something less than 1 and negative. Okay. The reason for this is that you are dividing delta x over the norm of delta, and the norm of delta is the square root of delta x square plus delta y square. So this ratio here is less than 1. And again, with that guy here, you are dividing delta x over square root of delta x square plus delta y square, and this is less than 1. Here you were dividing delta x over square root of delta x square, which is delta x. So it's always 1 or negative 1. Okay, but here no. Here it's actually less than 1. But again, either positive, something less than 1 but positive, or something less than 1 and negative. Okay. And again, you will move the robot. If the robot is not close enough to the goal, you need to move it toward the goal. But the goal has x and y position. So you need to move your robot in x and y. That's why we have new route in x. So we will move the robot with this distance to this location in x and to this location in y. So the new point at which the robot will move to has a coordinate of new route x, new route y. So after this step here, this iteration, the robot will move to a new location that has a new coordinate in x and y. The coordinate of this location, the new location, is called the new route x. The coordinate of the y location is called new route y. Okay. So this will be, you know, as we did previously, you know, x old equal to x new. Oh, where it is, yes. So again, we are doing the same here. This is the old equal to the new, but the new has two coordinates, okay? Not just one value in one coordinate. And we add this point to the route. At the first step, the route has the start node. Now it has the start node and this new node. Okay, so let's do it. It will take time, but you know, let's do it. So we know, guys, that the location, our goal location is at, let me write down with you so we know that the goal location is at, we said what it was, yeah, no, not the start. The goal is at, yeah, 450. So let's see what's gonna happen based on that. And our start is at, where is our start, my friend? Yeah, is at 50. The start is at 50 and 350. Good. So let's basically do that together. Let's see what's gonna happen. So we're gonna put a breakpoint somewhere here. Oh, this is on dimension. So let's put a breakpoint here. Or here. Yeah, here. And let's run this guy. Okay. So basically we go into the first iteration because this condition was not satisfied. Okay, and after this first iteration, the robot will move to a new location. So remember, its previous location was at 50 and 350. Okay, it will move to 47 and 347. Okay, 347. Good. So let's continue. It's not that clear and it's not that imaginable. I understand like the previous. Then in the third iteration, we will move. Yes, we will move to 46. Of course, there will be some rounding because in the array there is no index called 46.3. There is 46. Okay, so we'll make some rounding. You see this guy. This is a rounding coming here with this floor. We didn't encounter this with one dimension because this operation here result in this operation result in positive 1 or negative 1. So there was no decimal stuff or real numbers. They were all integers. But here, because this guy is less than 1 and this guy is less than 1, so this multiplication here might not be integer. Okay, so we make some flooring here. Okay, so the new location of the robot is 46 and 345. Let's continue. 44, 344. Let's continue. For it will take time because the speed is small. Let's increase the speed. Let's make it 10. Okay, start from the beginning. So from the start, we will go to 43. At the beginning, we were at 50 and 350. Now we will go to 43 and 342. Then we will go to 39 and 333. It's much faster. Then 38 and 323. And 38 again and 313. Let's have multiple of them. Okay, now 83 and 209. Let's increase more. 140 and 180. Okay. Remember, we want to go to 450. So the thing on the right or left, left, yeah, which is 214 now, should go to up to 400. And the thing on the coordinate on the left, which is 180, should go to 50. So this guy should increase, this guy should decrease. Let's see. Okay, yeah, this guy is decreasing and this guy is increasing. Yeah, 330, 112. So as we said, the one on the right should decrease and the one on the left should increase. Yeah, we decrease to 70 now for the coordinate on the right, and the coordinate on the left, it increases to 347. Now 392, just 80 steps away from 400. And the other guy is actually 50.7. Okay, so we are very close to 50. Okay, 395. This now, it will bounce now for the one on the left. It will bounce. 399 and 52. 400.6 and 42. This one become far. So there will be some bouncing. Okay, until we reach some compromise, we can say something within the tolerance. Now it's bouncing, and we will see that on a graph after a while. Okay, what happened? Yeah, 452, maybe. Let's see. Okay, so it's bouncing. So probably for these particular constants or parameters that I choose, we're gonna exceed the number of iterations. Okay, but you see, guys, that we are going towards the goal. Yes, there is some bouncing at the end, because of, again, the speed, maybe. Okay, maybe other parameters, like for example these zeta and eta, the two constant of the repulsive and the attraction force. But I think here the main influential parameter is speed. So maybe with 10 is much high. So maybe with 3 we can reach with better accuracy. Let's see. We can try that. This is the last trial. I want to show you something very nice. A very nice example, with no bouncing. So let's see. Okay, so let's still. Okay. Okay, now we are going up here and down here. Okay, up and down. Up on the right, down on the left. I'm sorry, up on the left, down on the right. Yes. Up on the left, down on the right. Up on the left, down on the right. Good. We are close. Okay. The one on the right should be 50, by the way. So we are six steps away. This one is 30 steps away from 400. Let's see. Okay. 393. 50.6. That's very good. 399. 49.5. 401. 51. Okay, we are very close. But again, maybe for this one here, again, the number of iterations. But we are bouncing with a limited distance. Okay. It's really hard to to get fine-tune parameters that will just throw your robot to the goal directly from the first time. You should have some bouncing. Okay, I think you got the idea. It doesn't. I didn't see something from the first time, but I think you got the idea. Okay, guys. So after this here, so we're gonna see. Let's continue. What we have. Okay. Good. So this is actually now the goal, which is moving, and here it's reaching its goal. And here is the bouncing that I was telling you about. You see, guys, there is some bouncing. This is why, because of the choice of the speed. Okay, it will stop after some time. Don't worry about that. This bouncing actually we saw in the when we were tracing the gradient descent code. These values that are very close to the goal. So it's now bouncing. It will stop after a while. It may take a while, but it will stop eventually. Good, we have finished. So this is another way to represent such map, such big map, which is really nice. There is another way to represent it. It's something called the Quiver plot. I will not go for the details of the Quiver plot. So this is the start node. Actually, when you see a big arrow, this is actually, you see, guys, this arrow here is there is an obstacle. So these arrows here shows you what should be the direction of the robot? If it's, for example, here, it should go in that way, away from the obstacle, away from the obstacle. And the length of the arrow tells you how much force. So a closer to the obstacle, a higher repulsive force. Away, lower repulsive force. And if we, zoom in, and this is the goal location, by the way. If we zoom in here, you guys can see this. This is stuff. This is actually the bouncing. Okay, so all these are points that the robot would just bouncing around the goal. Okay, but this is acceptable. That's nothing bad. And here is here is, as I said, he just stopped. Okay. Okay, let's now examine the values of the zeta. Yeah, this zeta, which I choose 1/700. Let's try 1/10 and see. We don't need to. We just want to explore. Yeah. So now I will set zeta equal to 1/10. Yeah, because basically we can't see. No, not the repulsive. The repulsive force. So here the repulsive force is very small. When I choose here zeta equal to 1/10, it was 1/700 in the beginning. Okay, 1/700 is much lower than 1/10. So if I increase zeta to 1/10, this will increase the attractive force. And it will be much, much, much higher than the repulsive force. So that the F will be approximately equal to F attractive. This will be neglected. That's why we see the total force very similar to the here is the attraction force. You got this, guys? Yeah, they are very close to each other. Okay, so if you choose very high value for zeta, like 1/10, this might affect the repulsive force. It will be neglected. If we choose it, for example, 1/10,000, this will decrease more compared to 1/700 zeta. In that case, if repulsive, if a total will be approximately equal to F repulsive, let's see, because the attraction force become very, very small. Look, total potential, that stuff here, and here is the repulsive force figure. Just to compare them to each other, they are identical, almost identical. Why? Because the attraction force is, because of the bad choice of zeta, it becomes very small compared to the repulsive force, so that the total is just the repulsive. This is very bad, because now again your robot will just slide down, and it might not reach the goal, because this is a flat region, as I said. Okay, let's try this. Let's try it and see what's gonna happen in that case. So let's try. Let's stop that. Okay. Let's stop after this point. the quiver plot. What? Oh yeah. Yeah. Look. So it can't move forward because there is nothing. This is a flat region. Okay. This is just a flat. So it goes away. So this is the robot goes away from the obstacles, but it just stuck on a flat region and it can't go to the goal because this dark blue here is just a flat region. You understood this guy or it's not clear? Any question about this? Clear?
So in order for it to not get stuck like that, we have to add both the attractive force and the repulsive force?
Yeah, they are all the time they are added together. But if you choose the zeta very small, the attraction force equal to zeta multiplied by something. So if zeta is very small, if zeta is zero, what should be the attractive force? It will be zero, right? So when we add those together, the repulsive plus the attractive is zero. So F will be equal to the repulsive. So you will have this problem. Here we didn't select it as zero. We just choose it with a very low value. Okay. Such that there is numbers, I mean, they are not zero in the attractive array, attractive force, but they are very neglected. They are much less than the values in the repulsive array, so that F is approximately equal to the repulsive force or the repulsive array. You got that?
Yeah, thank you.
Okay, now let's learn how to draw this ball that is sliding down, which is really nice, and it's really good to know how to draw that. So after this step, guys, we called this gradient descent algorithm. We know the route. This route array contains all the point upon which the robot will land in its way to the goal. Now we want to draw this map with a ball that is sliding from the start node to the goal node. Let's see how to do that. Okay, first we wanna plot a ball, okay, in MATLAB. So of course this ball will represent our robot, okay. So let's open another nice sphere. How to draw a sphere or a ball in MATLAB. So this is actually the command or the functions that we use. So let's this command here will draw these two lines. These two lines would draw a sphere centered at 0, 0, 0, and the radius will be 1. So let's just execute or evaluate that part here and see what we have. Yeah, you see, guys. So this is a ball or a sphere centered at 0, 0, 0. Because if you look at any axis here, it's from -1 to 1, -1 to 1. If we look to another axis, which is x, again, -1 to 1. So the center is 0, 0, 0. This is clear? And basically the radius is just 1, half of that length here. Okay, this is if you want to draw a unit sphere centered at the origin. How about if you wanna, and the resolution, if you wanna make it, so let's draw this again. So we represent the sphere here as, you know, rectangles. Okay, it's not a very fine sphere. It has rectangles. You guys can see, can imagine this. It's not a perfect sphere. Now, to increase the resolution of this sphere, we should decrease the dimension of these rectangles. And how to do that? Using this very small step. So just add the number of rectangles here. So this will be 50 by 50 rectangles. The default here is 20 by 20. So this should have, if we execute these together, we'll generate two plots. Yeah. We can compare both. Yes. I think it's clear. Both are centered at 0. Both have a radius of 1, but this has 50 by 50 faces. So it's, you know, it has more resolution. And this has 20 by 20 faces. So it has less resolution. Now, what else? And of course, this will be much higher resolution. So let's draw that as well. Evaluate selection. So this is 100 by 100. This is 50 by 50, and this is the naughty one, 20 by 20. This is how to increase the resolution. Now, how to draw the center at a specific point, or how to increase first the radius. If you want to increase the radius, you should multiply x and y and z by the radius. For example, if the radius is 5, you should do that. So this will generate a sphere, a ball, with 100 by 100 faces, centered at 0, 0, 0, but the radius is not 1. The radius will be r, 5. So let's evaluate this. Look, guys, 100 by 100, but the center is still 0, 0, 0, but the radius is 5. This is 5, from -5 to 5. Good. Now, how to draw not at 0, 0, 0. For example, if we want to make the center at 2 in x, 2 in y, and 0 in z. So you subtract the center coordinate. So for example, the center coordinate x is 2, so subtract 2. The center coordinate y is 2, so subtract 2. Center coordinate of z is 0, so subtract 0. Of course, it will be the same. So let's do that. Let's do both, just to see the difference. One is centered at 0, the other is centered at 2, 2, 0. So this is, yeah. This one is centered at 0. 0 in x, 0 in y, and 0 in y, yes. And here is x, again 0. Now this one here, again the radius is 5. Now for z, for z it's 0, the center is 0, but for y it's -2, and for x it should be also -2. This is x here. You see, guys, -2 in the middle. Okay, so this is how to do that. Now let's go back and do our stuff in our very long. Yeah. So okay, we define here the sphere. You can call this x, y, z. That's fine, but I call it sphere x, sphere y, sphere z. The radius is 20. Okay, you can choose any radius. The bigger, you know, you will see it better. That's it. On the map. Okay. So this is the radius. Now I will, you know, move it a little bit. So the radius everywhere is 20. That's fine. But why we did this here? Let's first do it like this. Okay, so to make it very clear. So now the center of this sphere is at 0, 0, 0. Okay. And let's draw the stuff. Let's apply everything. Let's remove all these. Even from here it's removed. Okay. We didn't change this. 1/700. Okay. So half of the ball is under the map actually, because the center of the ball is the location at which the robot will go, the point in the X and Y points in the route. So to make all the ball above the map, we should lift it up by its radius. We should shift it up by its radius in the direction of Z. This is the dimension that have the problem, the Z dimension. For that reason, we added here R. So to shift it up by R. Okay. Now, if we do that, you will see the difference very clear. You will see the ball, all the ball is above the map. Look, guys, all of it is above the map. There is, tiny bit. This is just a bug in the GUI of MATLAB, not our coding. Okay. Now let's go to the details of the drawing. So here we are drawing the ball, the sphere, and at this point, the center will be 0, 0, 0. Or the center will be 0, 0 and 20 in Z. So let's verify this. Yeah, here is the ball at 0, 0 and 20. The center in Z is 20. Then we add some, beauty to it. Just forget about those. This is just the ball color. You can change it to whatever you want. It's added some lighting in the figure, so you can just ignore those as well. Here I am drawing the goal on the map using a green and asterisk as an asterisk. So let's, yeah, because I stopped it. So here is the ball still at 0, 0x, 0y, and the radius in Z. And here is the goal. The goal is just an asterisk to mark this location. Okay, so now let's go step by step. Now I will change the location of the ball. I will make the center of this ball at the first location the robot will land on, which is the start point. So let's see. So route of 1, because I now is 1 in the first iteration. Look, guys. So this is the start point actually. Okay. Then we move the point or the ball to the second point in the route, whatever it is. So it moves a little bit. You see that, guy? Did you notice the movement? I hope you can. Let's continue. So with every step, it's moving a little bit because there are many points out there. Okay. Let's see. Yeah. Point by point, point by point. Point by point. Point by point. Then we will have this bouncing, man. Okay, until we finish all the points inside the route. Okay, but it will take time until finish all the point out there, as we said. Then we'll move to this point in the code. Okay. We will not, explore the quiver plot, this last plot that I showed you, but this was important. This how to draw this map, how to draw the ball, how to slide the ball, or move the ball according to the route. Okay, so you can create your own simulation environment in the future. Okay, guys, any question? Any question?
Mr. Mustafa, and the 2D artificial field, what was floor for again? What did that do?
What is what?
It was like a line of code that had said floor and then
Okay, yeah, this one.
yes. What does that do?
I will do. Okay, I will. So let's do it. Basically, I will show you why we need it. Okay. So, because we did. Okay. In the next iteration, we're gonna need it. Yes. Look here. Gx is actually an array. It's 400 by 600 array. And gy is another array, 400, 600 array. Okay. If you want to pick one element inside this array, you need the column number and the row number, right?
Mm-hmm.
Can this row number and the column number be float numbers, something like 1.1? Or it must be integer?
Well, it could also be a float number, can it?
No, if we can't. Look, let me give you an example on MATLAB very quick. So A equal to, it's a very simple array, 1, 2, 3. Okay. We want to read A of 1, the first element. Yeah. The first element, which is 1, right? A of 2, second element, A of 3, third element. But you can't say 1 or 1.1. Where is that?
Oh,
There is,
I know.
you understand?
Yeah.
So basically, you want to read gx of something and something. Row number, column number. Okay? You have the route, but x is, as you see, 47.9. And y is 347.7.
So it would
But
round, right? To like
so
48.
yeah, we will floor them down, we will round them down. So we will read gx of 347 and 47.
Oh, okay.
Okay. So we need this. We didn't have this floor stuff in the one-dimensional example because the location of the robot is always integer. Okay, because this operation here, this operation always returns an integer. Okay, always returns an integer, but here it's not returning an integer. This is not an integer. This is something less than 1. It might be positive, it might be negative, but it's not equal to 1. Okay.
I got it. Thank you.
Any other
That's-
question?
Yeah, just on that what you're talking about. Why use floor instead of just using round? What's the
That's why you
reason
can do.
behind it?
Yeah, you can do stuff. You can do
Oh, okay.
round. You can go. You can take rounding up or down. Okay. Here I am taking the floor all the time, but you can do rounding up or rounding down based on the decimal number. That's fine. Basically, there are some approximations here. Okay. First, you choose the attraction force. You choose the repulsive force. You choose the constants in eta and zeta in both repulsive and attraction force. You choose the speed. And by the way, the speed here can be float number as well. But I didn't do that here in one dimension. But you can do in one dimension a float number speed. So the speed here, for example, is equal to 1. You can make it 1.1. And at that time, you will need to make a floor. Actually, there is a floor, but it has no value because it has no benefit because the current position is always integer. But if you choose a speed, a float number, then you need the flooring. Okay. Any other question, guys? You need to understand the code. I may ask you in anything of that. Okay. Forget about the homework. Maybe within 2 weeks we will have our first midterm. And the midterm, I probably will give you something in that topic, the artificial potential field. Okay, it may be a design problem, which you will do everything from scratch. The choosing or the selection of traction force, selection of repulsive force, everything from scratch. Okay. So you must have this in mind.
So, Professor, is the midterm going to be mostly abstract questions, or are they going to be just coding, like programming
Coding.
They're
Coding.
going to be coding? Got it.
Yeah, coding. This course is coding. It's all about coding.
All right,
Okay.
and will there be a time limit then, like 2 hours or 3 hours?
I didn't decide even on the exam date, but maybe it's take-home exam. But of course, at that time, you should, guys, promise me that no connection with anybody, even the internet. Okay, you have your own codes, your own thinking, and you just do it.
Yes, of course. Thank you.
We'll see. Okay.
Do you think you explain the difference again between the 1D and the 2D for the delta x divided by the norm delta? Because this one
Yeah.
gives you just negative values, you said?
I will. No. I will. Let me do it with on the tablet.
Oh, okay.
So let's share the tablet. You see the tablet, right?
Yes.
Okay. For the 1D stuff, let me write down the equation. If you go back to the coding of the 1D, you have some variable called delta direction x. Which represent how much you need to move in the direction of x. We calculate this based on that equation. It's equal to something called delta x over norm of delta x. Okay, delta x This is some variable that delta x is some variable that you calculated at that time. Just review the code and you'll find it. But what is norm of delta x? This is basically square root of delta x squared. This is equal to delta x over delta x, right? So this will, but this guy in here is always positive because this is the result of this square root. But the variable itself might be negative. So this guy might be positive or negative. It doesn't matter. If it was positive, this will give you positive 1. If delta positive. If delta is negative, this will give you negative 1. Okay? That's in 2D. How about, that's in 1D. How about 2D? In 2D, we'll do the same. But now, we have two of these, delta x and delta y. So delta direction x equal to delta x over norm. Now, norm of what? Of delta x, delta y. Because the location has two coordinates now. And delta direction y equal to delta y over norm of delta x, delta y. This is equal to delta x over delta x squared plus delta y squared. This is equal to delta y over same stuff, delta x squared plus delta y squared. So this guy is less than 1, right or wrong? It must be less than 1, right?
Well, why is it less than 1?
Because just pick a number. Because basically this guy, the numerator is larger than the numerator. Pick a number for x, let's call it x. X is equal to the square root of x squared, right? Because it's just equal to x. So what if we add something here? Anything. So this must be less than, right? Let's take a numerical example. 2 is less than or equal to the square root of 2 squared. But 2 is less than 2 squared plus 1. Right or wrong?
That's right.
Okay? Same as here. Delta x.
So delta x and delta y will always be smaller because you're adding the delta y squared.
Yes, yes. Oh, and also delta y. In the case of delta y, we are adding delta x. Okay?
Right.
Okay, that's why this guy is less than 1 and this guy is less than, it's not equal to 1. That's why we need the floor or the rounding, whatever you choose, floor or round, that's all are the same. Okay, there is no preference in that. Yeah, so in 1D it's positive or negative 1. In 2D, no. In 2D it's less than 1. Okay, either also positive or negative. Because this guy here, this denominator is always positive, of course. But the numerator might be positive and might be negative. You got it?
I think I got it.
Okay.